In this video, I'm going to introduce you to drawing simple Lewis structures for chemical compounds. A Lewis structure is a two-dimensional representation of a molecule. Eventually, we will use Lewis structures to try to infer something about the three-dimensional shapes of molecules. For a molecule like nitrogen trifluoride, NF3, we draw a Lewis structure by first coming up with an electron budget that factors in all of the valence electrons from nitrogen and 3 fluorines. Nitrogen has 5 valence electrons. Each fluorine has 7, and there are 3 fluorines in this molecule. So for fluorine overall, we expect a contribution of 21 valence electrons. Altogether, the number of valence electrons from nitrogen plus 3 fluorines gives us our total electron budget, 26 electrons. This means that we should show 26 electrons in the Lewis structure for nitrogen trifluoride. Next, we're going to position nitrogen and 3 fluorines with the least electronegative atom in the center of our molecule. The least electronegative atom is nitrogen. We're going to draw the Lewis symbol for nitrogen. We'll show it with 5 valence electrons. 1, 2, 3, 4, 5. I'm going to position fluorines around this central nitrogen atom in such a way that the unpaired electron on each fluorine will align with unpaired electrons on the central nitrogen. A fluorine perhaps here with 7 valence electrons, and then in each of the other 2 locations around nitrogen. From this layout, I'm going to start connecting lines. I'll connect unpaired electrons with straight lines that represent bonds between the central atom and the peripheral fluorines. At this point, after I've connected all unpaired dots, 2 things should happen. For one, we expect that all 26 electrons from our electron budget are depicted in this structure. And for another, we want to be sure that each atom in this molecule, nitrogen and each fluorine, feels like it has 8 electrons around it and satisfies an octet rule. Eventually, we'll talk about exceptions to this octet rule, but for right now, we'll try to draw molecules that have octets around every atom. So, let's count the total number of electrons shown in this structure. Every line is going to count as 2 electrons, every dot an individual electron. Around each fluorine, we find 1, 2, 3, 4, 5, 6, 7, 8 electrons. Another 8, another 8, that's 24 electrons. There are an additional 2 around nitrogen. So we have shown just as many electrons as our budget requires. What's more is that every one of these fluorines we just recognized feels 8 electrons around it. We say that the bonds between atoms represent a shared pair of electrons. A shared pair of electrons that each atom feels as though it's got. Therefore, both the fluorine and the nitrogen that share this pair of electrons feel as if they've won that pair of electrons outright. The central nitrogen feels a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons around it as well, taking into consideration all of those shared pairs and this pair of electrons that it's got up top. This pair of electrons that isn't bound to anything that sits on this central atom is just a lone pair of electrons. There are lone pairs of electrons in each of the peripheral fluorines too, but it's really going to be this lone pair of electrons on our central atom that we're going to be concerned about moving forward. We say that the central nitrogen atom in nitrogen trifluoride has 3 shared pairs of electrons with 3 different fluorine atoms and 1 lone pair of electrons. Overall then, every atom in this molecule feels an octet. It feels as though it's got 8 electrons around it. Thus, we expect that this is a good Lewis structure to represent NF3. Next, let's draw the Lewis structure for molecular oxygen, O2. Oxygen has just 2 atoms in it. Our electron budget looks as follows. Each oxygen has a total of 6 valence electrons. So our Lewis structure overall should show 12 electrons. There is no central atom here because we are only dealing with 2 atoms in this molecule. So I'm going to draw 2 Lewis symbols for oxygen, each with 6 electrons around it. And I'm going to choose to draw my Lewis symbols in this fashion. I'm going to connect an unpaired dot at the central plane between 2 oxygen atoms. And now I'm going to evaluate this Lewis structure to see if it satisfies our general guidelines for drawing. So for one thing, this Lewis structure does depict 12 electrons. The bond represents 2. There's 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So our first stipulation can be checked off. However, if we evaluate each oxygen atom in turn, either one feels only 7 electrons around it. 1, 2, 3, 4, 5, 6, 7. This is true for both oxygen atoms in this Lewis structure. Therefore, this is not yet a valid Lewis structure. We're going to have to do something more. The something more takes into account these remaining unpaired electrons on each oxygen atom. In order to feel like each oxygen has 8 electrons or satisfies an octet, perhaps these 2 oxygens could simply share one more pair of electrons with each other. To depict that, I'm going to move these 2 electrons up into the plane between these oxygen atoms and draw another bond between them. In this manner, now each oxygen feels 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And we have therefore satisfied the second stipulation of drawing a Lewis structure. We can use multiple bonds between 2 atoms in order to try to make every atom feel as though it's got an octet. We refer to 2 shared pairs of electrons, like in this structure, where 2 pairs of electrons are shared, as a double bond, 2 shared pairs of electrons. For our last Lewis structure that we'll draw in this video, let's consider ozone, which has the chemical formula O3. For our electron budget, we have 3 oxygen atoms, each again with 6 electrons in its valence. So our Lewis structure should depict 18 total electrons. There is a central atom in this molecule, but the central atom isn't all that important because all 3 atoms are oxygen. So I'm going to draw 3 oxygen atoms right next to each other. From here, I'm going to start connecting dots. I can connect a dot between these 2 oxygens and these 2 over on the right. And I could count up the total number of electrons here. We've got 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. So we've satisfied our electron budget. But once again, our oxygens, at least on the peripheral sides, don't feel an octet. 1, 2, 3, 4, 5, 6, 7 for the oxygen on the left and the oxygen on the right. So what do we do? Well, one possibility might be to connect these 2 electrons to each other. And that is a good idea, except for the fact that this molecule can't bend that way. The radii of these oxygen atoms is simply too small to allow for that to happen. So that's not a possibility. We'll get rid of that. Perhaps instead, we can start drawing double bonds. Suppose that I moved one of these electrons that are paired up on the central oxygen somewhere else. If I need to, I can move electrons around, just like we saw when we drew double bonds between oxygens in the O2 molecule. So let me move that electron over to this vacancy on the oxygen to the right. Now, I've got an electron on my central oxygen atom and on the oxygen atom to the left that need to be paired up. So I've made a double bond off to the left. Let's count up how many electrons each oxygen feels. The leftmost oxygen feels 1, 2, 3, 4, 5, 6, 7, 8. The central oxygen feels 1, 2, 3, 4, 5, 6, 7, 8. And the oxygen on the right, 1, 2, 3, 4, 5, 6, 7, 8. We still have 18 total electrons, but now every oxygen feels like it has an octet. So this looks like a good Lewis structure. But let's backtrack for just a moment to the original Lewis structure that we'd sketched out before we started moving electrons around. I arbitrarily chose to move an electron from a central oxygen atom to a vacancy on the oxygen to the right. What if instead I'd moved an electron from the central oxygen atom to a vacancy on the oxygen to the left? We might imagine performing a similar action, this time with the oxygen in the center and the one on the right forming a double bond. That looks like this. Sort of the mirror image of the structure we drew up above. In this image down below, we still have 3 oxygens, each with an octet, and a total of 18 electrons depicted. Except in this one, the double bond between oxygen atoms is on the right. So which one is correct? Is it the top? Or is it the bottom? Well, it turns out that they both are correct. There's nothing invalid about either one. So therefore, both of them must be valid Lewis structures. It's almost like this double bond could be either on the left or the right. And in fact, the actual structure of ozone is an average of these two valid Lewis structures. We refer to the existence of multiple valid Lewis structures for the same molecule resonance structures. The existence of resonance structures is incredibly important for chemistry and understanding chemical behavior, given the three-dimensional shape of a molecule and the layout of electrons. In these resonance structures, the bonds between oxygen atoms are neither double nor single, but somewhere in between. We can calculate a bond order for these resonance structures. The bond order in a Lewis structure gives us a count of the number of shared pairs of electrons relative to the number of electrons that are spread out amongst atoms. To calculate bond order, we'll count up the total number of bonds between two atoms of given types and the number of bonding partners that those two atoms of given types represent. For example, in ozone, we refer to the oxygen-oxygen bond order. The total number of bonds between oxygen atoms in ozone is, in either Lewis structure, 1, 2, 3 total bonds. The bond order is calculated by dividing 3, the total number of bonds, by the number of bonding partners. In other words, how many pairs of oxygen-oxygen are shown in any given Lewis structure. For the topmost Lewis structure as a model, we have one set of partners on the left and another set of partners on the right. There are 2 partners sharing 3 bonds. The bond order between oxygens and the ozone is 3/2, or 1.5. Neither bond in ozone is a single bond, nor is it a double bond. It's somewhere in between. And the actual Lewis structure of ozone is an average of all the possible valid Lewis structures that we can draw for this molecule.